Okay, section 9.2 is testing claims about two proportions. In this section, we're going to use methods for testing a claim about two population proportions and constructing a confidence interval to estimate the difference between those two proportions. This section's based on proportions, but we're going to use the same methods we did in Chapter 8 for using the normal distribution to approximate the binomial and for dealing with probabilities or the decimal equivalent of percentages. The notation here for our two proportions: if you see a subscript of 1, then you know that those values came from your first sample, whatever you're going to call your first sample. So this would be the population proportion for the first population, the sample size, the number of successes, p hat, q hat. All of those numbers are the same as they were in Chapter 8, only now we're going to have one group with a subscript of 1 and the other group with a subscript of 2, so that we can differentiate what information comes from population 1 and population 2. Now, in order to do some of the number crunching behind the scenes, what we're going to see is pooled sample proportions. And how we calculate the pooled sample proportion is we take the sum of the successes from both groups and divide by the sum of the sample size for both groups. And this is called a pooled P. We pool our values. The requirements that are necessary is, first of all, we have to have two independent simple random samples. And then also the number of successes has to be at least 5 and the numbers of failures at least 5 from both of those groups, Group 1 and Group 2. How we calculate the test statistic for the two proportions for testing the null hypothesis that Group 1 is equal to Group 2. This is how we would come up with the test statistic, and this is where we use the pooled P when calculating the standard error. But you don't have to worry about how to do that because we're going to use a two proportion z-test on our calculator. This is just what's going on behind the scenes within the algorithm of the calculator. So here we assume that the null hypothesis P1 minus P2 is going to be equal to 0. Isn't that the same way of saying that P1 is equal to P2? If you subtracted those two proportions, wouldn't you get P1 minus P2 equals 0? That's what we're doing for our null hypothesis here. You'll see our alternative hypothesis. They're going to be writing it in terms of this instead of just having a number there. We'll be looking at P1 is not equal to P2 for a two-tailed test. P1 is less than P2 for a left-tailed test, and P1 is greater than P2 for a right-tailed test. But this is how we get to the test of hypothesis on the calculator. We hit Stat, go over to Tests, and then we go down to the two proportion z-test, and I think this is number 6. I'm not going to swear to it though. The p-values are automatically calculated by the calculator. We'll stick with that. And then the critical values, you can use a table to do it, or we can use the inverse t. And we're going to have to put in our alpha level and then our degrees of freedom. The confidence interval for measuring estimate, we're going to have our lower bound, which is our point estimate minus the error, and then our upper bound would be the point estimate plus the error. That hasn't changed in how we calculate confidence intervals. On the calculator, instead of doing a two proportion z-test, we'll do a two proportion z-interval. This is for the confidence interval. Be careful. If you're performing a test of hypothesis, make sure the last letters on the test are test. If you're doing a confidence interval, make sure the last letters are INT. Now let's look at a sample problem, and I think this is where things will start making sense. The question is, do people having different spending habits depend on the type of money they have? 89 undergraduates were randomly assigned to two groups and were given a choice of keeping the money or buying gum or mints. The claim is that money in large denominations is less likely to be spent relative to an equal amount in many smaller denominations. Let's test this claim at a 0.05 level of significance. So there's your alpha level. Alpha is equal to 0.05. So here's the sample data. Group 1 was given a $1 bill. This is the number of people out of Group 1 that actually spent the money out of 46 people. And then there's the number of people out of Group 2 that spent the money. So here's X1, N1, X2, N2. We do have to check the requirements, make sure that the requirements are met to be able to do this test. First of all, we have a simple random sample, and we have at least 5 who spent the money and did not spend the money from each of the groups. So N times P is greater than or equal to 5 for both groups, and so N times Q is also greater than or equal to 5 for both groups. So we're okay here. We're testing a claim, so that means we need to write a null hypothesis here. Our null hypothesis will always be that P1 is equal to P2 if we have two proportions. Group 1 was given the larger denomination. The claim is that money in large denominations is less likely to be spent than having change in your pocket. So what would our alternative be? How would I phrase the alternative here? P1 is what then? P2. Greater than, less than, or not equal to. Group 1, remember, is the money in the large denominations. Group 2 is change. Group 1, we would say, is less likely to spend money than the group with change. So let's actually do this on a test. So we're going to need our calculator. We're going to hit Stat, go over to Test, and this is going to be a 2-prop z-test, number 6 here. So our first number of successes. Success, remember, is people who actually spent the money. We had 12 out of 46. And out of the second group, 27 people bought the gum or mints out of 43. Our alternative is going to be less than, so now we want to calculate this probability. So out of these results, our output then is going to look like this. Arrow going down here means that I have more information below, so we need to take a look at that and just see what it is, and it's the rest of the data. So this was our input, this was the output, and we'll call that from screen 1, and this is from screen 2. We got to this by just scrolling down. So what is our p-value here? If we're going to use the p-value method to test this, what number here would represent our p-value? This is the name of the test. This is our alternative hypothesis right here. This is our test statistic. And this number right here is the p-value. And you say, wait a minute, a p-value is a probability, right? The p-value is the probability of getting the results that we got with this information up here, the data, assuming that the null hypothesis is true. P-values, because its probability, can't be bigger than 1. Well, it's not because of this e to the -4 right here. What that means is we actually ended up with a p-value of 0.00024. This is scientific notation. So is this a large p-value or a small p-value? Very, very small p-value. So based on this p-value, would we reject or fail to reject the null hypothesis? We would reject the null hypothesis because the p-value, remember, is the probability of getting these results assuming the null is true. There's a very small probability of getting these results based on our assumption. Therefore, we have to throw out our assumption because we got these results. We reject the null hypothesis, which means, in essence, we accept the alternative. So our conclusion here, there is sufficient statistical evidence to prove the claim or support the claim that people are more likely to spend money when they have smaller denominations available in their pocket. From the input screen, I highlighted calculate, and then I hit enter, and then I got these output screens. And yeah, I just hit the arrow down to go from output 1 to output 2. Because of that arrow right there, I knew that I had more information to follow, so I scrolled down, and this is what was on the bottom. The p-value is going to be that first p. This p right here has a hat on it. That's the proportion or the percent of people who spent the money from group 1, and this is the percent of people who spent the money from group 2. There's an overlap right here because I only had 2 things below that p hat. So it may look like there's more p's than are actually there. If I used my test statistic, I would reject the null hypothesis because that test statistic is more than 3 standard deviations below average. I knew that that was going to be a teeny tiny probability because that test statistic is way out there. It's easier to use the p-value. In my math lab, they also want you to give them the critical value. So you could compare the critical values. The critical value for a 0.05 level of significance for a left-tailed test, it would be -1.645. Let me draw a picture that kind of illustrates what I'm talking about. If we were to use the critical value method, I would actually need to go through the process of finding the critical value, and then I'd look at the graph of a normal distribution, because these are z-scores, and it was a left-tailed test. So my critical value would be right here at -1.645. But my test statistic put me way out here at -3.5 roughly. So the p-value is the area to the left of that critical value, but that critical value fell in the red zone. That critical value there was -1.645. So there's 2 options to use whenever you're making a decision about whether or not you should reject or fail to reject the null hypothesis. The first option is the p-value method. If your p-value is less than whatever your alpha level was, and your alpha level has to be predetermined before you ever start the problem, and if they don't tell you, we use alpha equals 0.05. The p-value method says if the p-value is less than alpha, reject the null hypothesis. The critical value method says if your test statistic falls to the extreme side of the critical value, then we'll reject the null hypothesis as well. Here, extreme side means smaller, but if it was a right-tailed test, extreme side would mean larger. And those are on the videos. I review those in the videos for 8.3 and 8.4.